Yes, okay,
Right.
we're set. Very good. Okay, so my task over the next few minutes, and I don't have a whole lot of time, which is hard for someone who talks so much. I'm going to talk about sample preparation and storage considerations. And just as a caveat, I would say these are really critically important steps of which we rarely ever talk about unless you're in the lab and you talk with people in the lab about how they do things. And so it's my pleasure to talk about these today and maybe give you some of my recommendations. The nice thing is that there are many ways to skin the cat, and what I'm going to tell you, maybe only one or two of them, but there are a host of other ways to do it. And so my advice is always to try your hands with these. The very first step in any lipidomic studies is to try and get a sample ready for the mass spectrometer. And one of the most typical things that one uses is a solvent extraction technique. And I would say it's really hard to underestimate how important this step is, because it is the step which gives you a high degree of purification of the sample. It removes all sorts of nasty things like proteins and gives you lipids, because many lipids, but not all, as we'll talk about that, can be extracted with a miscible solvent system. Now, you heard from Gerhard very nicely explained two of these. One is the Bly-Dyer technique, one based in chloroform, which you form a monophase, then you break that up to form the two-phase system, and you extract the lower level. And I'm not going to tell you anything different than what Gerhard told you. This one is probably one of the most widely used techniques to isolate lipids. It is hardly ideal. It's not perfect. Now, a technique which we have used extensively in my laboratory to isolate lipids, and I would say lipids of interest, has been one using a solid phase extraction technique, which was preceded by only working with those compounds which were soluble in methanol or ethanol. And some people have talked about this miscible solvent that's adding methanol or ethanol to sort of crash out the proteins. And as an extraction method, I wouldn't use extraction as the word, but as a way to prepare the sample. But if one uses this technique and then that follows that by a solid phase extraction technique, we've often used reverse phase. That's another way to prepare the sample for the mass spectrometer. So this isolation of the lipids from the biological matrix is a critically important step. You have a couple different strategies of using an immiscible solvent. If your class of lipid is readily extracted, this is a wonderful way and really can purify your sample to a great extent and make it easily prepare it for mass spectrometry. I would add, the only thing is that you might think about tailoring this immiscible solvent system in a way that's best for your lipids. For example, if you were trying to analyze the polyphosphonosides, this has been a very difficult thing to do by mass spectrometry. And I would say largely because of the extraction techniques. They're poorly extracted with immiscible solvent. And here's a recent reference of actually coming out of Phil Sanders and at Eli Lilly, where they acidified the biological matrix with one normal HCl, very high concentrations of acid, and then did a Bly-Dyer type extraction. And they found very efficient extraction of these polyphosphorylated PI species, which were difficult to do otherwise. So that is sort of tailoring the method. Now, that's a dangerous thing to do, to extract with one normal HCl, because you're going to start hydrolyzing lipids with that. And so you have to neutralize your extract fairly quickly. So what you are what I'm sort of proposing for you is to consider the lipids, and maybe your lipids of interest have different solubilities. And virtually insoluble in water is squalene and the cholesterol esters. They just almost have no water solubility at all. Squalene, if you hadn't thought about it, you saw that in the biochemical intermediates in the steroid biosynthesis by Bill. But squalene happens to be very abundant lipid in hair in the shaft of hair. So if you want to measure squalene, you can measure it there. But these are not soluble in water at all. In fact, it's a problem working with these things if you have aqueous systems. And then as you go down to more and more esters, triglycerides, diglycerides, phospholipids, highly ionized, and single lipids, and then the highly derivatized steroids like cortisol, so on like that, they're much more soluble in water than they are in organic solvents as you get down to these. So there's a change of solubility and extractability of lipids. There are some lipids which you cannot extract by organic solvents. I would put into that the lysophosphatidic acids. Some claim that you can, but it's very difficult to extract unless you really acidify the solution. Sphingosine 1-phosphate, the lysophosphatidylinositols, or I can tell you from a world of experience, like 40 years of experience, leukotriene C4, you cannot extract that lipid from an aqueous system. You must deal with it by crashing out, for example, proteins and other unwanted compounds with maybe methanol, and then do a reverse phase, solid phase extraction method to get leukotriene C4. So the problem is that not all lipids are going to behave identically. And the method you use to extract the lipid will largely determine the class of lipids you're going to be able to study. But fortunately, lots of methods are available to use this extraction method to purify your sample. Okay. And once again, to emphasize, not all lipids can be extracted by miscible solvent systems. Now, I want to talk about the, modifying this neutral lipid, modifying your extraction. In this case, I'll emphasize neutral lipid extractions, and in spite of what Michael says. Now, they're not my favorite lipids, but here I'll give another example with them. And this is comparing Blydier to an isooctane ethyl acetate extraction, very similar to maybe using MTBE, but not with the methanol. So the recovery of triglycerides is excellent with both of those techniques, but the recovery of phospholipids is very poor with isooctane and ethyl acetate. And you can see that on the TLC separation on the right side of the slide. You see at the origin, the isooctane ethyl acetate, we don't have a blur there at the origin where the phospholipids are, but you do have them with the diglycerides. But all the other neutral lipids really behave quite nicely in terms of their separation and extractability. So we've used, for example, the isooctane ethyl acetate method when we go after the neutral lipids, because we can extract them and not extract interfering compounds like phospholipids quite as efficiently. And so, tailoring your extraction to the class of lipids you want is a very useful strategy. So my advice is very carefully consider what extraction method you use. There's nothing which is perfect, and perhaps tailor your method for the class of lipids. And I would say searching the literature is time well spent. Look at how the Blydier protocol back in 1959 was described, and the Fulch extraction, or if you want to extract blood without worrying about extracting hemoglobin, the Rosen-Oaklander method. And there are lots and lots of other extraction methods you can find in the literature, and that's advice and time well spent by looking at those. So let's turn now to storage of lipids and the native sample. Now, a lot of people say, well, I'll just extract the lipid, then I'll store that in the solution I extracted. Well, there can be problems with that. One can do it And in particular, if you have used a very tailored extraction method, which doesn't have a lot of other components present in it, that might still work quite well. What you worry about in storage is this chemistry right here. And this is just showing a lipid which has a homoconjugated diene. And when free radicals are present, you can pull off a proton from that diene system and then attack with oxygen to form these hydroperoxides. Now that's a pretty favorable reaction when free radicals are present. And free radicals can be present, for example, in a tissue. They can also be present just as with dissolved oxygen, because oxygen is a diradical, and it can actually initiate some of these reactions. So what you do when you take your sample, you try and lower the temperature, reduce chemical reactions. If you're worried about oxidation of the sample, well, remove oxygen. This chemistry is oxygen dependent. So just remove oxygen. You do that by degassing solvents and also storing your sample under argon or nitrogen, dry nitrogen. Now, to remove oxygen, there's a lot of dissolved oxygen in organic solvents. And so you have to actually remove them by a degassing strategy, vacuum or purging with helium. And so that's an active process you must think about before. And possibly what you want to do is to remove the solution which you extracted the system, your lipids in, and redissolve them in a degas solvent, and then store them under nitrogen. Now, time of storage is really pretty important too if you're worried about these oxidation reactions, or if you're worried about hydrolysis. Another important feature about lipids is that many lipids are esters, and they're subject to acid and base catalyzed hydrolysis. So removing traces of water can be very important too. So once again, perhaps removing the solution you extracted them in and redissolving them fairly quickly in a degas solvent where there's no water. So that could be a good strategy. Now, sort of a caveat is about, well, if you remove the solvents already dry, why don't I store them like that? Well, that can be done too. You would certainly want to seal them probably in an ampule under argon, because when you seal them in a cap or a rubber stopper, you're going to have oxygen come in from the air. And sometimes you don't know if that's happened, and so that can be a problem. Now, some lipids, in particular, when they have very minor amounts of an ionic lipid, for example, like a phosphate ester of maybe a PI phosphate ester, they can be almost irreversibly lost on glass surfaces because they form ionic bonds with a little bit of ionic bonds on the glass. Now, I know that Walt Shaw spent a lot of time looking at glasses, and he's found that this shot glass from Germany, in which they by vapor deposit quartz on the surface of glass, minimizes that problem. And if you want to go to the trouble trying to get shot glass, that would be okay to probably store them dry. Most people don't do that, store them dry, because you spread the lipid over a large surface and you're asking for reactions with atmospheric oxygen to take place. What about storing the native matrix? Well, I'm storing frozen plasma. That should be perfect. Well, there can be problems with this as well. And I'm going to show you some data that's about 30 years old. This is from Jason Morrow and Jack Roberts at Vanderbilt, and they stored some plasma for several months at -20. So that's sort of the freezer compartment of a refrigerator. And what they saw when they analyzed these samples, a 50-fold increase in prostaglandins. And this paper was first published as in fact they were prostaglandins. Later, much later, not much later, but shortly thereafter, they found that what they were producing was a whole series of related compounds to prostaglandins and they called isoprostates. And these are oxidized arachidonic acid isomers, which come from free radical oxidations. And here's some of the chemistry involved. Turns out to be a very favorable reaction. Surprisingly favorable, surprised everyone how favorable that was. If you want to read this paper, it's from 1990. It's useful for any student to read old literature, mainly because some of us published papers back in the 70s even. Anyhow, you can form, for example, isomeric or free radical oxidized products even in solid plasma stored at minus 20 degrees. And storage of samples is something that probably you have to work with anyhow, but worry about these and what your analysis is coming up with. I would say consider adding, I call it a sentinel. I would have called it Paul Revere, but I think our British colleagues would not have liked that. This is something you add to the sample that can indicate that there is oxidation going on. So for example, if you were worried about isoprostates, you might add stabilized tope-labeled arachidonic acid initially and prior to storing the sample, and especially if it's a stored extract. And then if there is any oxidation going on, you're going to see that the oxidized products are deuterated. So this is a good way to evaluate that process. Okay, let me turn now to the solvents you're going to use to extract and store samples in. They're not perfect evil either. Worry about the solvents you buy, and don't buy, for example, of course you wouldn't, technical grade solvents. They're cheap, but they're going to contain a whole variety of solvents, which is going to interfere with your analysis. There's also worry about some of the solvents you get because of the presence of compounds or absence of compounds which might protect that solvent. So like we always say, use fresh solvents. So buy them in small quantities, not in bulk, so you can throw them away if you find a problem. Now, there are some specific problems that lurk with halogenated solvents, and I have pointed this out previously, and I'll just take a few of these slides out of this presentation I did for Avanti with chloroform and methylene chloride, and then a little problem about methanol. So chloroform can decompose by light, and we worry about this in Denver because we have a high flux of photons from our beautiful blue skies, and it can form phosgene, but also the presence of transition metals such as iron. Now, normally we add a stabilizer, for example, ethanol, to chloroform to prevent this, and there's another reaction that can happen if chlorine is formed. But this is the reaction of phosgene. For example, aminophospholipids react with phosgene, and they can form a carbamate type intermediate, a chlorinated, which then adds to nucleophiles, or anything which is present in your sample. And this is an example of anything which is present. This is an extraction that Chris Rates did with chloroform, which has not been stabilized, and there was phosgene present. And here's his lipids. Look around, molecular weight 960, and he was isolated some complex lipids, and you see them there. And you can see at high mass at 1021, they were later identified as glutathione adducts of phosphatidylethanol. So the question was, were those naturally occurring or were those artifacts? Well, he took the same sample and extracted with chloroform, and they weren't there. So these were formed by the reaction of glutathione, a nucleophile, with the adduct of phosphatidylethanol with phosgene. So methanol can cause problems, and methanol seems pretty simple, but you can oxidize it if you do something like heat it up to high temperatures, like flame seal a sample. You can form formaldehyde. So with formaldehyde is present, it's going to react also with the aminophospholipids to form Schiff base adducts. And here is a sample come out of the Avanti laboratory is their internal standard. They didn't seal the sample. You can see there are some sodium adducts as well as the protonated compounds. You always get sodium adducts when things are stored in glass because of the high content tenth of sodium in glass. But when they flame sealed these things, they saw plus 13 adducts. Well, that's a very strange mass adduct. And that turned out to be the Schiff base of these, and the Schiff base plus sodium of this PE adduct, because when they flame sealed, some of the methanol was coming out the top of the ampule, and it was burning to formaldehyde, condensing, going down into the sample. So when they cooled the methanol, they got rid of that. Dichloromethane, although we used it a lot to substitute for chloroform, we got this bottle of chloroform from Fisher. Was supposed to be HPLC grade, no preservatives. This must be wonderful stuff. But unfortunately, dichloromethane is made from carbon tet by adding chlorine gas, and you form methylene chloride and 2HCl. That's a commercial process. And they add amylene to stabilize it. Well, what does that do? It reacts with any free chlorine. We ran into this bottle. We took this was our standard mixture of triglyceride internal standards dissolved in MTBE. And you can see there's all these the internal standard is 771, and then all these reference standards we use to make the calibration curve, 48, 0, 50 with 1, so on like that. When we dissolved this sample in that dichloromethane, it shifted to this weird mass spectrum of the standard was gone. There 48.0 was there, but then there were some new lines like 84, 841 and 843 and 920, and there were no unsaturated triglycerides present. That's because what was happening is you were forming these chlorine adducts with our internal standard and our triglyceride. They formed this chlorinated adduct, and that's the 920 and 841 is the chlorinated adduct of the deuterated internal standard 44.1. This reaction with chlorine is very, very rapid. And so if there's any chlorine present, it's going to form the chlorinated adduct. So the amylene is reacting with that and reducing free chlorine present. So, and then of course, the oleate of cholesterol oleate is going to be react with oxygen as well. So summary, no extraction system is going to be perfect. You're going to have to make some compromise. There's no way you're going to look at all lipids in a single extraction system. You have to think about what lipids are you going to look at. Maybe just the major lipids, maybe just the phospholipids, maybe just the eicosanoids. Lipids themselves have different solubilities in water, and people come into this problem if they're going to make up an internal standard solution of a cholesterol ester, and they think they're going to make them up in methanol water systems. No, they're not soluble. They're going to be in the glass. And so you're going to have terrible internal standards. You need to add the internal standard in a totally organic system. So tailor your extraction to the class of lipid you're studying. Always think about removing oxygen by degassing solvents prior to extraction, possibly, but certainly prior to lipid storage. And also maybe add a deuterium labeled molecule to check for free radical oxidation, useful thing. There can be artifacts present in your solvent system. Phosgene is present in some batches of chloroform, and you should probably check for it. Don't trust the label, which says that there's no phosgene present. You can form methanol by reactions with formaldehyde, and methylene chloride may contain chlorine if it's unstabilized, and an M+2 may not be something which is more saturated, but could be the chlorine 37 isotope. So anyhow, those are some of the suggestions I might make for storing solvents and preparing your extraction. Be glad to answer questions.